Welcome everyone to CECS 228. This is a continuation of Basic Structures Part 1, sets and their operations. So last time we got a look at some basic definitions that have to do with sets. Today we're going to take a look at the operations that are defined for sets. Starting with the union, let A and B be sets. The union of A and B, which is denoted with this A and what appears to be, kind of looks like a U, but that is read as union B, is a set of all elements found in either set A or set B. That is, the union of A and B is defined to be the set of all elements such that X is in A or X is in B. If you have n distinct sets, then if the union of A1 with A2 down to AN would be all elements such that the element is either found in the first set or the second set or the nth set. So as long as it's present in one of the n sets, it'll be part of the union. And something that I added here is a notation that is written alternatively. Instead of listing out all the sets that are part of the union, we might simply write it as union with a starting index, so starting at I equals 1, an ending index n, and then A sub I. Right, so for example 14, they're asking us what is the union of the following sets? They don't actually label these, but I'm going to go ahead and call this A and B. So therefore, if we have A union B, we're looking at the set of all elements such that they are present in at least one of them. And so, for instance, we have element 1 is present in both. Element 2 would be part of B as well because it's present in B. Element 3 would be part of the union. Element 5, and that is it, right? Because all of these are present in at least one of the sets. If we take a look at what is the union of Z plus and 0, the set containing 0, that's referring to the union of the positive integers with 0. So essentially what we're looking at is 1, 2, 3, up out to infinity, union the set containing 0. And the result of that is going to be a set that contains 0 and all the positive integers. If you recall, this set has a special name. This is the set of natural numbers. And one more. Here we have 3 sets that we're taking the union of. We're taking the union of Z plus with Z minus and the set containing 0. So we take the positive integers, the negative integers, and 0 and put them all into one set. What are we going to have? Well, we're going to have everything from negative infinity up to 0 out to positive infinity. So that is essentially all of the integers. And the union of those 3 gives us the integers. Another operation that we can have for sets is intersection. So if you have 2 sets A and B, the intersection, which is denoted by this symbol, it looks like a U that has been flipped, is the set of all elements that are found in both set A and set B. That is, the intersection of A and B is all elements such that the element is in A and the element is in B. And again, if we want to generalize this to n distinct sets and take the intersection of those n sets, then that would be the set of all elements such that the element is found in the first set and it's found in the second set and it's found in every set up until the nth set. And to write this notation more compactly, we can also use the intersection symbol with a starting index I equals 1 all the way to n and have A sub I. Let's look at example 15, which is asking us for what is the intersection of the following sets. This is the same A and B sets that we saw in example 14. And now if we take the intersection, we're looking for all of the elements that they share in common. So for instance, 1 is present in both A and B, so 1 would be part of the intersection. 3 is present in both A and B, so it's part of the intersection. And then 5 is not present in B, so it can't be part of the intersection. And 2 is only part of B, but not part of A. So therefore, the only elements that are part of A intersect B is 1 and 3. They're 1 and 3. If we take a look at part B, they're asking us what is the intersection of the positive integers with the set containing 0 only. So if we look at what do they share in common, well, they don't share any elements in common, right? 0 is not a positive number, so it's not part of Z plus. And none of the elements in Z plus appear in the second set. So in this case, the intersection would be the empty set. They don't share anything in common. And then finally, we have part C, where we're taking the intersection of the reals with the negative integers, and this third set that is defined to be the set of all integers such that the integers are greater than 3. So essentially we're looking at integers -2, -1, 0, 1, 2, so on and so forth in this third set. So the way that we can attack this problem is focus on one intersection at a time. So what I mean by that is we can focus just on the reals intersecting the negative integers. Just to give ourselves a visual, if we're looking at the real number line, and let's say this is 0 and we have -1, -2, so on and so forth. Well, the reals would mean everything on that number line, right? Every number on that number line. If we think about what are the what are the negative integers? Well, these are just -1, -2, -3, so on and so forth. So the place at which both of those sets intersect, meaning the elements that they share in common, are really only the negative integers, right? So that first intersection boils down to it being the negative integers. All right, so now I'll bring over this third set. So I'll switch my pen there. And we said these are all the integers that are greater than -3. So that would be -2, -1, 0, 1, so on and so forth. So if we want to see what elements these two sets share in common, well, Z minus has only negative elements, so that would have to be -2 and -1 that they share in common. And that would be our final answer. And I haven't really been highlighting our answers, boxing them, but I'll do so now. That way there's no confusion as to what is the final answer. Okay, so let's take a look at the definition of disjoint. Let A and B be sets. We say that A and B are disjoint if the intersection of the two sets results in the empty set. That means that if you take A intersect B, then you don't get any elements in common, and therefore you get just empty set or null set. And we already saw an example of that in part B of example 15. If you take the intersection of the positive integers with the set containing 0, no elements were shared in common, so we got the empty set. So that means that Z plus and this set are disjoint. Here are some other examples of sets that are disjoint. If we try to take the intersection of the positive integers with the negative integers, they're not going to share anything in common. So that's going to be disjoint. If we have a set that contains, for instance, the elements 1, 2, 3, and another set that contains the element A, when we try to find what do they share in common? Well, that's nothing. So again, those are disjoint. And these two sets are also disjoint. It might seem like they have something in common, but the first set contains only one element and it happens to be another set, whereas the second set contains one element and it's the element A. So they actually contain very different things. If we think back to the analogy of the folder and a file, the first set would contain a folder, while the second set would contain a file. So those are not the same type of element, therefore they don't share anything in common, and that means that they would be disjoint. Here's another operation that is defined between two sets. Again, let A and B be any sets. The difference of the sets A minus B, which is denoted as A minus B, is the set of all elements that are in A but are not found in B. So in our set builder notation, what it would look like, it would be A minus B is the set of all elements such that the element is found in the set A, but the element is not found in set B. So if we look at example 16, here we have those two sets with first being 1, 3, 5 and second being 1, 2, 3. And we're trying to perform the operation A minus B. So A minus B will take the elements in A, so 1, 3, 5, and eliminate any elements that are found in the second set from A. So for instance, because 1 is found in B, then we eliminate it from A. And then because 3 is found in B, then we eliminate it from A. And so at the end, the only element that survives is the element 5. And just to cross-reference with this definition to make sure that it satisfies it, 5 is an element that is in A but is not in B. And any other element could not have been kept as part of the difference because 1 is found in B and 3 is found in B. So only elements in A that are not found in B is 5. So that would be the result. And now what happens if we take the difference B minus A? So if we change up the order. So B minus A means that from the set B, we're going to be removing any elements that are part of set A. Okay, and so what that means is that we'll be removing 1 because 1 is present in A. We'll be removing 3 because 3 is present in A. And the only element that will survive is the 2. Okay, so again, 2 is an element that is found in B, is the only element of B that is found in B and not found in A. So that's the only thing in the only element in the difference. And we have one more. We're going to be computing B minus the intersection of A and B. So first, let's take care of the intersection. The intersection A with B would mean they share in common the 1 and the 3, right? So intersection would be 1, 3, which we also calculated in example 15. And so what does that mean? Well, it means that from the set 1, 2, 3, we're going to remove 1 and 3. So 1 is going to get eliminated, 3 is going to get eliminated, and we end up again with just 2. Alright, so as you can see from part B and C, we notice that B minus A gave us the same result as B minus A intersect B. So as a question that I'd like for you to consider, is it true that B minus A will always equal B minus A intersect B? So keep that in the back of your mind, and you'll have an opportunity to discuss it with your peers during the lab session. Okay, what about complement? All right, so here's another operation. We're going to let U be the universal set, meaning it's the set of all possible elements over which A is going to be defined, and A is the smaller set. We say that the complement of A, which is denoted as this A bar, is the set of all elements that are not found in A. So basically what that means, and I apologize that my printer didn't print this very nicely. We'll try to go over it. So the complement of A is defined to be the set of all elements that are part of the universal set such that they are not found in A. So to give ourselves a little bit of a diagram, let's say that in this box I have all possible elements that I'm considering, and we're calling that the universal set. And then let's say that set A is here, it encompasses certain elements of that universal set, but there are some outside of A that are, well, clearly not part of A. Well, the complement of A would be considering everything that is in the shaded region outside of the set A. All right, so let's look at 17 to solidify this idea. What is the complement of B if B is the set of all integers such that the integers are between 1 and 10 exclusive, meaning we're considering 2, 3, all the way down to 9. And the universal set is the set of all integers. Well, if the universal set is the set of all integers, and B is, again, just to write it in roster form, or using the roster method rather than set builder notation, B contains the integers 2, 3, down to 9. Then B complement is supposed to contain everything that's found in the universal set that is not part of B. So that would mean everything from negative infinity up until 1, and then we wouldn't include these and then move on to 10, 11, and anything out to positive infinity. So to give a set builder notation of those elements, we could say it is the set of all integers such that the integer is less than or equal to 1, or the integer is greater than or equal to 10. And that brings us to set identities. So just like we had equivalence laws for logical expressions, we have some laws that pertain to set identities. And these are, for instance, the identity law that says that if you take the intersection of any set with the universal set, that you'll get A, or that if you take the union of the empty set with any set, then you'll get A. We have domination laws where if you take A union, the universal set, we're going to get universal. If you take the intersection of any set with the empty set, then that's going to be the empty set. Some more commonly used ones are the complementation law, where if you take the complement of A, you're going to get A back. There are the distributive laws that are also pretty common. So if you have the union with an intersection, you can distribute the union into the intersection to get A union B intersect A union C. Similarly, if you have intersection with the union, You can have A intersect B, union A intersect C. Another very important law is De Morgan's law for sets. So De Morgan's law claims that if you have the complement of the intersection, then it becomes the union of the complements. And if you have the complement of the union, then it becomes the intersection of the complements. And so, again, I encourage you to read through the rest of the laws, but we are going to take a look at how to prove some of these first before we apply them to come up with other assertions. So in example 18, they're asking us to prove the second distributive law from table 1, which states that if you take the intersection of the union, then you have the union of the intersections, and we're going to prove it by definition. So the definition of when two sets are equal, okay, so right now I'm not even focusing on this expression. I'm just saying in general, if you want to show that two sets are equal, then by definition that means that A has to be a subset of B and B has to be a subset of A, meaning every element that is in A is found in B and every element that is in B is also found in A. So applying this definition, in order to show that this equation holds true, there are two things that we need to show. We need to show that the set on the left-hand side is a subset of the set on the right-hand side. And we also need to show that the set on the right-hand side is a subset of the set on the left-hand side. So we're going to be working towards those two parts of the proof, starting with this first one. All right, so to prove part 1, we're going to pick an arbitrary element x, which is found in A intersect B union C. Okay, now by the definition of intersection, the following is going to be true. That means that x has to be in both A and it has to be in this set, B union C. All right. Furthermore, by the definition of union, if x is in B union C, that means that x has to be in B or x has to be in C. And so we're going to say, by definition of union, we have that x is in A and x has to be in B or x has to be in C. That's this portion. All right. Now, we've boiled it down to a compound proposition, and we have a conjunction of a disjunction. So that means that we can apply the distributive property for logical connectives. And that means that we're going to say this is equivalent to having x's in A and x's in B, or x's in A and x's in C. Okay, so this is by distributive property for logical connectives. Now, let's focus now on what that is defining in terms of sets. If x is in A and x is in B, that means that x is in the intersection of A and B. And so hence, x is in the intersection of A and B. or X is going to be in the intersection of A and C because it's found in both sets. So X is in A, intersect C. And so just be careful with the symbols here. It's a very common mistake to replace the union for a conjunction the intersection for a conjunction or the union for a disjunction. Yeah, so you want to be careful that whenever you have sets and you're trying to describe a relationship of two sets, that we are using intersection or union. All right, so now we have the statement X is in this set or X is in the second set. And whenever we have that statement, that means a union. It's in the union of the two sets. So i.e., X is in the union of A intersect B with A intersect C. And this is by definition of union again. Okay, so what have we shown so far? We've shown that if X is an element of A intersect B union C, then it ends up also being an element of A intersect B union A intersect C. Okay, so hence, or I'll say notice, this means that if X is in A intersect B union C, then X will be in A intersect B union A intersect C. Now, how did we pick X? We chose it arbitrarily. And because we chose it arbitrarily, it's going to be true for any other element that we pick that is part of this first set. So since X is arbitrary, the result holds for any element X, or for every element X. So i.e. what that means is that for any element X, if X is in A intersect B union C, then X is going to be in A intersect B union A intersect C. And that is the definition of subset. So A intersect B union C is going to be a subset of A intersect B union A intersect C. And this is by definition of subset. Okay, so far we've proved the first part of the goal. It was show that the left-hand side is a subset of the right-hand side. We've shown this. We now have to go in and prove that the right-hand side is going to be a subset of the left-hand side. But this is something that I'm going to let you guys do in your breakout rooms that you guys can discuss together with your peers. And so we're going to move on from example 18, but once you have shown that both 1 and 2 hold, then this equality is going to hold. I want to include one more example that illustrates this method of proving that two sets are equal. So example 19 is actually showing us to prove that the complement of the intersection is the same as the union of the complements. And so in order to show that, we're going to have that same type of goal that we had in example 18, meaning we want to show that the left-hand side is a subset of the right-hand side and vice versa. And so I'm going to start by showing that this first statement is true. And we're going to do so by picking an arbitrary element x that is part of the complement of A intersect B. And by the way, I have already written down the whole proof. That way we can just focus on the logic. Okay. So we're going to pick an arbitrary element. And then what that means is that x is not going to be found in the intersection, and that's by definition of the complement. If you recall, the complement means it's the set of all elements that are part of the universal set that do not form part of whatever set you have here. So in this case, that set is A intersect B, so that means that x is not part of that set. Now what that further means is that if we make the claim x is in A intersect B and we negate it, then that statement is going to be true. Now if we focus just on what's inside of the parentheses on the statement x is in A intersect B, that statement is equivalent to the statement that x is in A and x is in B by definition of the intersection. But then we do have that negation outside of parentheses that we need to bring down. So that's where that negation is coming from. And now because we have a compound proposition with negations, we're allowed to use the equivalence laws for compound propositions. In particular, we can use De Morgan's laws to apply the negation to each of these individual claims. And so that what that would look like would be negation of x is in A, or, because we had a conjunction before and that has to change under De Morgan's law, so or negation of x is in B. Now, what that means is that x is not in A, right? Negation of the statement x is in A would be x is not in A, or x is not in B is true, because this expression was the same as, or is equivalent to this expression, and that expression was true. That means that x is not in A or x is not in B is also a true statement. Now, what does that further mean? That means that x has to either be in the complement of A, right? If it's not in A, it has to be in the complement, or it has to be in the complement of B, and that's just by definition of complement. If it's not in A, it has to be outside of A, which is A complement. Now, because we have a disjunction, x is in this set or x is in that set means union. That means that x has to be in the union of A complement with B complement by definition. So what have we shown then? We've shown that if x is an element of the complement of the intersection, then x is in the union of the two complements. And since x was arbitrary, that result is going to hold for every element x. So that means that for any x, if, and I misplaced this parenthesis, if x is in A intersect B complement, then x will be found in A complement union B complement. That is the definition of subset. Okay? That shows that A intersect B complement is a subset of A complement union B complement. So that shows A. What would be left for us to show then is that now if we take an element, an arbitrary element that is found in A complement union B complement, then it is also going to be found in A intersect B complement. But again, that's something that I'm going to let you guys think about and work with your peers once we get to the lab session. Another way that we can prove set identities is by using the set builder notation and logical equivalences. So we're actually going to do that to prove this statement that A intersect B complement is the same as A complement union B complement. So let's start off with what is the definition of A intersect B complement using set builder. So that is the set of all elements such that the element is not found in A intersect B. Right, so it's part of the universal set, but it's not part of A intersect B. Furthermore, what that means is that it's the set of all elements such that X is in A intersect B with negation in front is a true statement, right? So in other words, we're negating the fact that X is in the intersection. And then what we can say, well, that is the same as having the expression negation of X is in A and X is in B. This is by definition of the intersection. Now, if we apply De Morgan's law for compound propositions, that means that this is the negation of X is in A or negation of X is in B. And so what that means is this is a set of all elements such that X is not in A or X is not in B. And well, that in turn is the definition of A complement union B complement. So as you can see, it's nearly identical to the steps that we took in example 19, but we're cutting out a lot of the explanation that's given in English words. We're just relying solely on the definition by set builder notation, and this actually allows us to prove it directly rather than having to show it by subsets. And here's another method to show that two sets are equal. That is to do it by means of a membership table. Membership table is very similar to a truth table, except that we use a 0 for meaning to represent that the element is part of a set, and 1 to represent, that an element is not part of the set, and a 1 to represent that it will be part of the set. So this is what I mean by that. We're going to create one row that has element A, well, I should say one column that holds the possibilities for an element being in set A, one column for possibilities of element being in set B, and one for C. Then because we are going to need the intersection A with B, the intersection A with C, and union C, we're just gonna, I'll just leave this whole space to represent A intersect B union C, and then this to represent A intersect B union A intersect C. All right, so let's think about all the possible combinations of zeros and ones for sets A, B, C. I could start off with just having the set present, the element present in set A, and then have it be present in set B and in set C, and then alternate that it is in B but not in C, that it is in that is not in B but it is in C, or that it's in neither one of those. And then we can repeat these combinations, but now for the element not being present in A. So we would have 1, 1, 1, 0, 0, 1, 0, 0. So now based on those combinations, what would be the membership, or rather, would the element be found in this set? Well, this would be the equivalent of, it's a 1 because it's an A, and it is found in B, or it is found in C. So because 1 or 1 evaluates to 1, meaning it is found in the union, And because 1 and 1 means that it is found in the intersection, ultimately this boils down to a 1. All right, let's take a look at the next combination. In this combination, the element is found in A. It is found in B, but it's not found in C. So in order for the element to be part of the union, it has to be found in at least 1. And so here we see that this disjunction will evaluate to 1 because it's found in B. So we have 1 and 1, meaning it's found in A and in the union. This evaluates to 1 as well. And so we just repeat that process. We have 1 and 0 or 1. So that is also 1. Then we have 1 and 0 or 0. Well, that's going to be a 0 because 0 or 0 means it's not found in the union since it's not found in either B or C. And then it is found in A, but it's not found in the union. So the intersection, it's not going to be found in the intersection, so therefore that'll be a 0 for its membership. And then we have 0 and 1 or 1, which is going to be 0. Then we have 0 and 1 or 0, which again is going to be 0. Basically, all of these are going to be 0 because they're not, it means that the element is not found in A. So if it's not found in A, it won't be found in the intersection. But just to be complete, I'll go ahead and write the full expression for each of those combinations. So we have that. Now what we're going to do is repeat the process, but now for this compound set. So combination of 1 and 1 or 1 and 1, well, that's going to be a 1 or a 1. So that's a 1. Then I have a 1 and 1 or a 1 and 0. Well, that's also going to be a 1 because we'll get a 1 here and a 0 or a 0 here. So that evaluates to 1. Then we'll have a 1 and 0 or a 1 and 1. This is 0. This is 1. 0 or 1 is 1. Then we have 1 and 0 or 1 and 0. Well, this is going to be 0. This is going to be 0. 0 or 0 gives us 0. And we have 0 and 1 or 0 and 1. That's also going to be 0. We have 0 and 1 or 0 and 0. That's also 0. And basically all these other ones are going to be zeros. We're going to have 0 and something else at all points. So 0 and 0 or 0 and 1, and that's 0. And then we have 0 and 0 or 0 and 0. So that is also 0. Okay, so what do we notice then? Well, we notice that this column that represents the membership of A intersect B union C is the same as the last column, which is representing the membership of A intersect B union A intersect C. So what that means is that they both of these sets hold the same elements, right? So because they hold the same elements, then they are equal. And I'll say that in words here, since the membership for A intersect B union C and A intersect B union A intersects C are the same, they hold the same elements. Hence, they must be equal. Right, so at this point, we're going to assume that all of the identities found on page 13 on table 1 have already been proven by one of the three methods that we described before. So we're going to take them as fact and instead use them to prove other statements, such as what example 22 is asking us to do. They want us to show that the complement of A union B intersects C is the same thing as complement of C union complement of B intersect with the complement of A. And so the key here is to start only on one side of the equation, of the equality sign, and then apply the set identities to try and reach the opposite side. So I'm actually going to begin here on the left-hand side. And what I'll say that this is equal to, not equivalent, but equal to, I'm going to say that that is equal to, I'm going to treat this focus on just the union. If we focus on just the union, De Morgan's laws tell us that the complement of the union is the intersection of the complements of the two sets. So if I break this up applying De Morgan's law, this is going to be the complement of A intersect the complement of B intersects C. Okay, then again, I'm going to focus on just the intersection at this point, the complement with the intersection. That is going to be equal to A complement intersect B complement union C complement. And I still need to keep parentheses around this because the intersection is being applied to the whole expression that results from the complement. So this is again by De Morgan's laws. Now, if you take a look at what the goal should be, what we should be reaching, we're very close. We have A complement intersect the B complement union C complement. So really this is just a matter of commuting the sets or changing the order in which they appear. So I'm going to simply commute the A complement with that group. And this is by commutative law, which is appearing here. Commutative laws allow us to move the order in both union and intersection. So I'm going to say this is by commutative law. And same for the B complement union C complement. I'll just commute those as well. And that is it. We've made it to the goal. All right, so let's move away a little bit from set identities and let's focus on the computer representations of sets. So there are multiple ways to represent sets in a computer. However, if we try to add elements to a set in an unordered fashion, that is going to make operations for intersection or union very costly. right? So instead, we're going to assume that the elements are being stored in ascending order, where the high or low value of the element is inherent to its type. So for instance, if we're storing integers, then we're storing from the smallest integer first down to largest integer last. So for instance, example 23, let the universal set be the set of integers 1 through 10, and they have an ordering a sub I is I. So like for instance, A1 is 1, A2 is 2, so on and so forth. We're going to be using a bit 1 at position I of a bit string to represent that AI is in a given set and 0 otherwise. So if we want to represent the elements of the universal set U using a bit string, we would simply have ones. We would have 10 ones to represent that there are the integers 1 through 10 present in that set. So with that representation, what bit strings are going to represent the subset of all odd integers? Well, let's see. 1 is part of the set, right? So basically what we have is 1, 3, 5, 7, and 9. So in bit string representation, that is going to be a 1, 0. Okay, so 1 is in the set, 2 is not. Then 3 is in the set, 4 is not, 5 is in the set, 6 is not, 7 is, 8 is not, 9 is, 10 is not. So that would be the bit string representation of the subset 1, 3, 5, 7, 9. What if we want to represent the subset of all integers exceeding 6? Well, all integers exceeding 6 would be 7, 8, 9, 10. And that's going to translate into the first 6 bits being 0. And then the last 4 bits being 1s. And finally, what is the complement of the set 1, 3, 5, 7, 9? This is essentially asking for all of the even integers in the range of 1 to 10, right? So the complement, just with the actual elements, would be 2, 4, 6, 8, 10. And using a bit string representation, that would be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Yeah, so 1 is not part of the set, but 2 is, 3 is not part of the set, but 4 is, so on and so forth. So now that we're using this representation, we can use disjunction and conjunction to find the union and the intersection of the set. So for instance, let's say that we have the set 1, 2, 3, 4, 5, which is represented by this bit string, and 1, 3, 5, 7, 9, the set of odd integers, which is represented by this bit string. If we want to find the union of the two, we would use disjunction of the 2 bit strings, and the disjunction would be defined bitwise, so bit by bit. What does that mean? Well, that means that, let me just write down the bit strings. We're taking 1, 1, and then 1, 1, 1, 0, 0, 0, 0, 0, union, which means disjunction with 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So what that, if you take 0 or 0, that gives you 0. It's not part of the set. 0 or 1, since it's found in at least one of the sets, that's a 1. 0 or 0 would be 0. 0 or 1 is 1. 0 or 0 is 0. 1 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. 1 and 1. So what set does this return to us? This is representing the set with elements 1, 2, 3, 4, 5, right? That's these first 5. then not 6, but yes 7, no 8, yes 9, and no on 10. So if you take a look, if we were to take the union of these two sets by hand, as humans that we are and that we understand these numbers, we would say the union is 1, 2, 3, 4, 5, then 7 and 9, which is precisely what we're getting with the bit string. So this is for the union. Now, what if we want the intersection? Well, in that case, we're going to take the conjunction of the two bit strings, where again, that means that they are simply being, the conjunction is being computed bitwise. So I'll rewrite the two strings. And then 0 and 0 is going to be 0. 0 and 1 is 0. This is 0, this is 0, 0, 1 and 1 is 1. This is 0, this is 1, this is 0, this is 1. So this is representing the set containing element 1, not 2, yes 3, not 4, yes 5, and that is it, because everything else is a 0. And if we check against the actual contents of the sets, we see that 1 is shared in common, 3 is shared in common, and 5 is shared in common between the two sets. Everything else would not be part of the intersection. Okay, and so that is how they're represented in a computer. And that actually is going to mark the end of our lecture for today as well. So have a wonderful day, and I'll see you guys next time.